Can I? Good. Yes.
So I think that we start. So today we have Ippei Obata with us to present a talk on axion search, current status and future. Ippei got his PhD at the Graduate School of Science at the Kyoto University in 2019. Since that, after 2 years, he was a postdoc at the Institute of Cosmic Ray Research of the University of Tokyo, right? And from April 2022, he is a postdoc at the Max-Planck-Institute for Astrophysics in Garching, granted by the Japanese Society for the Promotion of Science. And in October this year, you will move to Japan again, this time to the Kavli Institute of Physics and Mathematics of the Universe in Kashiwa, the University of Tokyo as well.
Yes.
Right? So Ippei is a theoretical physicist and a cosmologist. He's very well known in the field of the precisely axion physics and how can we constrain the properties of the axion field using cosmological data. So thank you very much, Ippei, for giving us this seminar. And you will have 45 minutes, roughly speaking, and after that we'll have some time for questions. Thank you.
Okay. Thank you very much for my introduction. So it's my great pleasure to have a talk in this IFCA, talk about the current status of axion search and discuss the possibility of the future expectation. Okay, let me start. So about introduction. So we are interested in the dark sectors in our universe. So so we know only 5% in our universe. So as a standard model, ordinary matter predictions, and the rest 95% is still wrapped in a mystery. So let's see. So around the 70%, so which is so unknown energy which causes the accelerated expansion of the current universe called dark energy, and we don't know that so that origins that could be a simply cosmological constant or some exotic object such as quintessence, and the rest of the around the 25% is so called dark matter, so which is necessary to to our galaxy to make a structure of the galaxy and then large structure, and so we don't know what is the origin of dark matter. So that could be the particle picture, that could be the WIMP or axiom, or the astrophysical picture, that could be the compact object such as matter or primary black hole. So in any case, that's central. So that's very important to identify with these dark sectors in our universe. And so there's a question. So are these sectors really independent components? What if they are related by a common origin? So, and up to now, a couple of the scenarios, the unified models for dark matter and dark energy have been developed by these theoretical scenarios. And today, I'd like to focus on one of the motivation. So the possibility that these dark sectors, dark matter and dark energy, could be explained by the one particle, so hypothetical particle axiom. And so axiom could be, it's known as promising, one of the promising candidates for both dark sectors. And this is the overview of today's talk. So, and first, I'd like to show you the background of the axion physics, axion search. So first of all, introducing what is axiom and how to search for that particle actions, and so to detect them. So what's necessary, and so mainly I'd like to focus on the search for axion-photon conversion. And later, so I'd like to introduce our current study, our current development of the axion search by introducing a new search method to search for the axions by using the photons birefringence effect. So recently detected in the observation of the CMB, and so discuss the potential testability in future measurement. Okay. So, and first of all, so I'd like to give a brief review of what is axion. The axion is known as a hypothetical pseudoscalar field, parity out field. And when people say axiom, there are mainly two kinds of actions. One is the original QCD axiom, suggested in the context of the quantum chromodynamics. And the next is more generic axiom-like particle, and predicted by the higher dimensional theories such as superstring. And the features of these actions, they are very small masses and weakly coupled to other matter sectors. We have never measured that's evidence of action. But so it's well known that the action could be a promising candidate for dark matter and dark energy, or anyway, dark sectors. So originally the action was proposed in the context of the CP symmetry in QCD. CP symmetry is characterized the matter antimatter symmetry in universe. So when we consider the theory of the quantum chromodynamics, so this is the Lagrangian density of the QCD sector. We have quarks and then gluons, and theoretically out of the CP violating term. And this coefficient theta is given by the phases in the quark mass matrix and the QCD vacuum structure. And that should be non-zero theoretically, but in experiment by the measurement of the neutron electric dipole moments, so we've never been measured this phase factor. It's strongly constrained, much less than order unity. So which means that why is symmetry strongly conserved, in the context of QCD? That's called strong CP problem. And so sorry for busy slides, but this is the solution of the strong CP problem, or of the solution. So originally suggested by Pecha and Quinn and Weinberg-Wilczek. So when we consider kind of a Higgs-like scalar field and consider the spontaneously symmetry breaking, so of the globally one symmetry. So for instance, at a typical energy scale, the symmetry breaking happens, and then the scalar field goes into the bottom of the wine bottle potential. And along this axis, there's a direction of the, Lamb-Goldson boson. So that's just axiom. And thanks to this mechanism, axiom induces theta term. So from the constant term to the dynamical term, and the value of the action characterizes the evolution of the theta term. And at a certain scale, the quantum compatibility effect happens, such as instanton. First of all, it's a massless, but from this time, the action gets its mass and goes to the minimum of its potential, simply characterized by the cosine potential. And based on this mechanism, we can effectively choose, the theta term, going to the zero by, so looking at the bottom of the potential. So this is the picture of how to solve the strong CP problem by axiom. Okay, so this is the features of axiom, QCD axiom. So why is the small mass compared with the WIMP? So when the mass is given by the QCD energy scale over the decay constant, the symmetry breaking scale. So it's evaluated around the microelectron volts. So that's much smaller than the GB scale or TB scale. And then secondly, so QCD axiom is weakly coupled to the standard model at low energy. So this is the interaction Lagrangian density of the axiom coupled to the other matter sectors. And why is the axion-photon coupling. That's the most popular term to think of the testability of axion. The other things are axion-nucleon coupling, axion-electron coupling, and axion-nucleon electric dipole moment. So anyway, these coupling strengths characterized by the inverse of the decay constant, the symmetry breaking scale of the axiom. That's much smaller than the kind of Fermi coupling constant. So that's why it's very hard to measure the smallness of this coupling strengths between axion and matter sectors. So this is the QCD axion window. So how much parameter spaces are constrained. So for lower decay constant less than 10 to the 8 GeV, that's excluded by the several kinds of stellar evolutions concepts. For larger decay constant range over the 10 to the 9 or 10 to 10 GeV, so that's preferable region. And especially this window is preferable in the context of the cold dark matter QCD axion. So that's the story of the QCD axion. So this is the case of the more generic axion-like particle, shortly called ALPS. So that's originally proposed by the string theory people, that's a victim. So which means that, so when we think of the higher dimensional theory and consider the compactifications of the extra dimension of the manifolds, depending on the how to compactify these extra dimensions, it leads to a bunch of axion-like particles, which order would be greater than 10 to 2 up to the 10 to 5. We don't know. But anyway, the apprehension about axion-like particles is predicted. And contrary to the QCD axion case, it predicts broader parameter space. This is because we don't know much about string theory. That's the reason. And this axion-like particle is also a candidate for dark matter as well. And today's talk, I'd like to focus on this more than QCD axion, this axion-like particles. The feature of axion-like particle that, so it's similar to the QCD axion case, but so it's a bit different. So the axion-like particles acquire their masses by the quantum non-perturbative effect also, and its mass is characterized by the instant action. However, so this is a very large value other than unity. So it's exponentially suppressed, which means that the axion-like particle naturally predicts very small masses more than QCD axion. And actually, recently, their guides predict the axion-like particle can be a fuzzy dark matter, so which could resolve the small scale crisis of the the galaxy or something like that. So the mass is around 10 to the minus 22 electron volt. And so we noticed that the QCD axion is not a candidate for this kind of fuzzy ultra-light dark. Okay, so I'd like to show you a mechanism, so how axion could behave as a cold dark matter. So this is called a misalignment mechanism or oscillation mechanism. The axion, when we consider the homogeneous component of the axion field, it obeys this kind of equation of motion in our universe. And this is the Hubble term, and this is the mass term. And in our universe, Hubble parameter depends on time. It's a decreasing function. So when mass is smaller than the Hubble scale, the Hubble friction term becomes dominant, and the axion is frozen at a certain point of the potential. It's constant value. However, Hubble parameter decreases in time, and at a certain time in the late time universe, the mass becomes greater than Hubble. At a time, the mass term becomes dominant, and it starts to oscillate along the bottom of potential. And it also directed away by the expansion of the scale factor. So after oscillation begins, the axion behaves as a pressureless matter fluid, which means that when we consider the energy density and the pressure of the axion fluid, the energy density is given by the summation of the the kinetic energy and the potential energy, and this kind of periodic function is cancelled out, and it obeys the ordinary matter component. On the other hand, the pressure is given by the difference between them. That's why the periodic function still arrives, and in comparison with the cosmological timescale, the oscillating time scales are much, much shorter than cosmological time scale. So that's why it's effectively, we can think of it as a pressureless fluid. So that's why pressure is smaller than gravity, and it could be a component of the non-relativistic fluid, and so action can behave as a dark matter component. And so how to find the abundance of the action density? So in the case of the QCD action, so it is given by only two parameters. So one is the initial condition, initial angle at the onset of oscillation. It's a model-dependent value, and then decay constant of the QCD action. On the other hand, so in the case of the action-like particle, so contrary to the QCD action case, we don't know the relationship between the mass and the decay constant. That's why we have a one extra degree of the freedom. So the mass and the initial field range, so which means that the decay constant of the action. So that's why in comparison with the QCD action, the action like particles have a much broader parameter space to play, the role of the dark matter. So, okay, let's see. So from now, let me move on to the how to search for the axion action particles. So one of the most conventional search is to think of the axion-photon interaction. So this is because the axion generically coupled to the photon via the topological term, just like this. And this is the coupling constant, the action field, and chance-time gauge field. And it is given by the production of the, in the production of the electric and magnetic field, just like this. And when we consider this kind of diagram, under the presence of the magnetic field, the action can convert into the photon or vice versa. So it is called the axion-photon conversion effect or Primakov effect. And up to now, a variety of astronomical experimental methods have been proposed to search for this axion-photon conversion effect under the presence of external magnetic field. So this is one mechanism of the axion-photon conversion occurs in a cavity. It's called the photon action dark matter resonance. So we assume the action is dark matter, which means that the action is a non-relativistic. So when we consider a large static magnetic field and one microwave cavity, the electric fields is created by action dark matter. So action dark matter oscillates in time with the frequency of the action mass. And if the photon's frequency corresponds to the mass of the action, QCD action in this case, so the photon's frequency around the gigahertz is correspond to the microelectron volt of action mass. The resonance happens inside cavity and the signal is amplified. So that could be a measurement of the QCD action dark matter. And so to cover a wide range of action mass, QCD action mass, so we have to scan the cavity mode frequency. So that leads to the several action horoscope experiments. So I'd like to show you the couple of action horoscopes for QCD action dark matter. The most, I think, popular, the relevant one would be ADMX, action dark matter experiment. But other than ADMX, several kinds of extended measurements have been proposed, such as Haystack and Max in Germany, and then Cadex in Spain. So the basic experimental setup would be considering the microwave cavity large cylinder, and we need a very superconducting Stokes magnet. And if the action dark matter come into this cavity, the microwave is amplified, and that could be a signal of the action dark matter, QCD action dark matter. So this measurement is very powerful to search for QCD action dark matter parameters, so around the mass of microelectron volt up to the millielectron. On the other hand, this is another mechanism of the axion-photon conversion. It's called photon action mixing. So we assume, so contrary to the dark matter case, action is assumed to be relativistic. So when we consider the background magnetic field, photon and axion provide a mixed state along its propagation. So this is a linearized equation motion for the axion and the photons. And this matrix is just a mixing matrix mixed between photon and axion. And so from this equation, when we solve it, we get conversion probability after propagating some distance. It is given by this equation. And so this graph shows the photon survived probability depending on the energy scale. And once we choose model parameter combination just like this, the photon survived probability starts to deviate from unity around the, for instance, order of TB. So depending on the parameter sets, we get lower energy cutoff scale, energy threshold, when the axion-photon conversion happens. And this is characterized by the this quality. Sorry, I forget to mention. The omega PL is plasma frequency, the effective photon mass, and this is action mass, and this is action photon coupling, and this is magnetic field anyway. So, and once we normalize these parameter sets, so it's relevant to the when we think of the action photon propagation in the astrophysical background. So the threshold will be around the order GB. Okay, so first of all, I'd like to show you most relevant axion photon mixing experiment. It's called axion helioscope. Its name is CAST experiment. It's a CERN axion solar telescope. So the setup of this experiment is that the aim of this experiment is to probe the axion thermally provided inside of the sun. Its typical energy scale is around keV, kiloelectron volt. And so once the axion flux come into this large cylinder where the superconducting magnet is there, the axion photon conversion happens, and it converts into the X-ray. So they are probing the X-rays created by the axion, solar axion. And so we can find the differential flux in keV, just like, sorry for the small characters, but we can find the solution. And this experiment, for now, the most relevant current experiment for action particles. On the other hand, we can also probe indirectly the action-like particles by looking at the high-energy astrophysical probes. So when we consider some, the high-energy astrophysical sources and which emit some cosmic rays, and this is the usual, observation. We would observe some kind of energy spectrum of cosmic rays. But when we consider the action for coupling, so under the background cluster magnetic field, axion photon conversion would happen. It would modify the observed spectrum of cosmic rays. So we can constrain this phenomenon from the several cosmic ray searches, such as X-ray, so by looking at them from AGN objects. So this table is a couple of studies looking at typical famous sources, AGN, and from here we can put a constraint on the bound of the axion photon coupling strings for typical mass ranges. And the sensitivities depends on the resolution of the spectrum and so the models of the cluster magnetic field. So that provides uncertainty more than the experiment mission. And current data is mainly from the Chandra satellite. It has very high resolution, more than probably XMM Newton. But XMM Newton is also used. So and so we are looking forward to the next generation's prediction, projected bounds from such as the Athena telescope. So that could be improve the coupling constraint order of magnitude better than the current bound. And so we can also constrain the action conversion from the gamma ray observations. So there are a couple of the studies so looking at the typical useful sources, and we get the upper bound on the action coupling constant with a typical mass range by the several gamma ray observations. So similar to the X-ray, so these sensitivities also depend on the uncertainties of the resolution of magnetic field. And constraint the magnitude of the coupling constant competitive with that case X-ray patches. And it would be possible to improve this constraint by looking at upcoming service such as CTA or something like that. And also, we have another constraint from gamma ray by looking at the supernova, in this case, the 1987A. So the very light actions are thermally provided inside the supernova, and the action fluxes propagates from the supernova to solar system, and along the propagation, the action flux converts into the gamma rays under the magnetic field. And so by considering a typical supernova simulations and considering the model of the magnetic field, so we can predict resultant constraint on the axion-photon coupling with respect to the mass of the axion. Okay, so this constraint is the most stringent amongst the current supernova measurement. Okay, so to summarize, so I'd like to show you an overview of the target spaces of the axion-photon coupling searches. The y-axis is the axion, the x-axis is the axion mass, so down to the 10 to the minus 30 up to the order 1 electron volt. Okay, so this yellow band is the theoretical parameter region predicted by QCD axiom, and so there are a couple of them constraints coming from the axion horoscopes such as ADMX. So on the other hand, so these wide range contour is coming from the measurement of the axion photon mixing, such as the axion helioscopes cast measurement, or the measurement of the supernova, and measurement of the cosmic rays coming from the AGN, Chandra, and projectable Athena constraint. But still, so we have a huge discovery space, and so we have to keep on trying to improve these kind of so measurements to achieve constraint better than the current bound. And so, by the way, so this is simple picture, but when we look at for instance this homepage, we could get much detailed overview of target spaces, so including the projectable variety of the missions. But it's a bit complicated. So okay, so that's introduction. So from now on, so at the rest of time, so I'd like to show you our recent study about new search methods for actions by using photons birefringence effect, not using the external magnetic field. So which means that the axion it's possible to behave as a birefringent material in our universe, such as crystal. So this phenomenon, photons birefringence effect by axion, has been already proposed. So which means that when we consider the axion photon coupling, the axion differentiates the phase velocity of circular polarized photon. So from this interaction, and when we look at the usual dispersion relation equation motion for the circularly polarized photons, left-handed and right-handed, so we get this kind of dispersion relation. But when we consider the axion photon coupling, it modifies the velocity, phase velocity, light speed of the two circularly polarized photons. And but magnitude is same between left and right, but sign is opposite between them. So when we think of the linear polarization is given by the linear combination of the two circular polarization. When one is faster than the other, the combined linear polarization is slightly tilted, just like this. So the action of the coupling leads to the rotation of linear polarized direction. So let's consider the birefringence by axion dark matter. So the axion dark matter, the axion field oscillates in time with a frequency of axion mass. And when we, according to the oscillation of the axion dark matter along the potential, the corresponding coupled photons, phase velocities are modified just like this. And when we consider the propagation of the linear polarized, the plane of the linear polarization, depending on the background motion of the axion field, the polarization direction is oscillating in time. So this axion dark matter induces polarization rotation, and it also oscillates in time with the frequency of the axion mass. And the typical frequency is around, for instance, when we normalize the mass is around 10 to the minus 14 electron volt, it corresponds to the order 1 hertz, 1 second frequency period. So that's very interesting. If we could measure this birefringence signal by methods of the experimental or astrophysical approach. So and I'd like to show you our current research about optical cavity experiment. So, we have launched a ground-based tabletop experiment, dark matter action search with ring cavity experiment, shortly called dance experiment, at the University of Tokyo. So this is the schematical setup of the optical cavity. So this is the mirror, and so this is the incident laser beam, and this bow-tie-like mirror configuration can sustain the rotational orientation of photon polarization. So we have to think of the parity flipment when the beam is reflected by mirror. So to sustain the effective one polarization direction, we need this kind of bow-tie-like configuration. And that's why we can effectively extract the polarized signal, birefringent signal from this resonant cavity. And finally, so we can get great sensitivity level of the axion-photon coupling. And now we are doing a prototype measurement. It's called dance action measurement. It's very compact. It's very tabletop. So it's very short and compact and tabletop experiment. So even if the prototype experiment, this sensitivity can achieve the current CAST experiment. And in the ultimate version of the dance mission, it could achieve the sensitivity with mass less than 10 to the minus 9, 10 to the minus 10 electron volt, 2 or 3 order magnitude better than the current astrophysical constraints. So that's our proposal, one proposal. And this is another way how to search for the action dark matter by using the optical cavity. So recently, we are up to prepare for the action search by using the real gravitational wave detection. The laser interferometer gravitational waves, it's just observing the gravitational waves by using this kind of Fabry-Perot cavity. So which means that this measurement this experiment just measure the phase difference of the laser beam. And if axion dark matter exists, it also provides the birefringent phase difference. And to pick up the birefringent signal provided inside the Fabry-Perot cavity of the gravitational wave detector, we just put some optics, just like the half wave plate or something like that, at the endometer of the detection port of the Kagura detector. Kagura is the Japanese gravitational wave detectors. And once we, so we put these optics, so we expect to get the constraint on the action of coupling with a broader mass region corresponding to the millihertz frequency to the kilohertz frequency of the action mass. And now if we also apply our technology to the other kind of, so current or next generation's gravitational detectors, we can achieve the great sensitivity level of the action coupling constant with several, depending on the experimental configuration of the gravitational detectors. So that's another proposal. And so this is the story of the action at the dark matter. But when we consider the action dark energy, it also provides the birefringence with a cosmological distance level. So we are looking at CMB birefringence by action dark energy. So axion with mass smaller than the current hyperscale, it's not oscillate. So mass is super small. That's why the Hubble friction term is still dominant. And it's slowly lowering on the slope of potential over the cosmological time scale. And if action is responsible for dark energy, so it makes the polarization plane of the CMB rotate from the dust scattering surface. And its rotation angle is given by the combination of the action coupling times the field displacement. So between our action field and action field at the dust scattering surface. So, and actually, it's been already proposed. So it provides the parity odd E mode and B mode polarization CMB correlation function. So, And when we think of the parity vibrating interaction such as action coupling, it produces the this kind of parity of EB relation. So it's typically given by the production of the birefringent angle times the our known CMB EE and BB angular power spectrum. And so we have also, if we think of the primordial EB angular correlation function, we have it, but usually unless we think of the parity vibrating theory in early universe, we simply assume it's zero. Anyway, so this is the way of searching for birefringence by looking at the CMB angular power spectrum. And actually, so we have been able to get a non-zero EB by previous measurements, but its value was not so reliable because of the systematic error, just miscalibration of the instrument angle. But recently, so Minami and Komatsu proposed a way to calibrate the systematic error angle by using the polarized emission from the galactic foregrounds. So which means that when we consider the birefringent angle is coming from the rust scattering surface, it's not related to the, it's not related to the polarization coming from the Milky Way, just like foreground. So by looking at the multi-frequency range, multi-frequency range, and we can separate the information between the miscalibration angle and intrinsic beta. And finally, they found non-zero value of the beta at a statistical significance of 2.4 sigma level. And recently, it's very timely. So this statistical significance is upgraded. So the first one is they used the public release 3 data, and recently, so your team proposed to, improve this value by using the public release 4 data, and statistical significance is increased up to 3 sigma. And very recently, so by using the combination of the data and Planck and double map, so they also improved the beta up to the 3.6 sigma. So that's why that would be exciting. So if it's finally confirmed, it's definitely a tantalizing hint of the parity vibrating physics such as axiom. And actually, we can give some implications for the action search by using the cosmic birefringence. So from this relationship between the beta birefringence angle and the action parameters, coupling constant, and field displacement, we can constrain the parameter space of axion-photon coupling with respect to the action mass. So this figure shows the parameter, the parameter region of the action-photon coupling with very, very low mass axion. And axion with mass less than 10 to the minus 33 electron volts, that's the region of the axion dark energy. And so the birefringence measurement just constrain the parameter of the very ultra-right axion as dark energy. So, and this is the background story. And so in the last couple of slides, I'd like to show it's a very theoretical, but so it's a very nice opportunity to introduce my recent work. So how to extend this idea to the other parameter range of the axion. So okay, let's see. So when we reconsider the axion dark energy model, we consider nearly flat axion cosine potential, so nearly flat potential to realize the slow roll motion of the dark energy. However, to realize the very flat potential, we need a large field range of the axion, characterized by the decay constant. And this value is very much greater than the Planck scale. So it's very weird in the view of the theoretical side. So it's very hard to realize this value from the effective field theory of the high energy physics. So, and also to get a measured beta, when we consider the action of the coupling given by the several model parameters, this is fine structure constant. This is anomaly question over decay constant. So we need a large anomaly coefficient is required. So more than unity. In the case of the, for instance, QCD action, this value is around the unity. So this large value is a bit strange. So in the view of the theoretical side, so we might need a bunch of the, for instance, the fermion sectors coupling to action. So to resolve this problem, we have suggested suggested multiple field action model. So not only the single field, but what happens if we consider the superposition of the, for instance, two field action model. We consider two action time potentials and two fields, and by considering the superposition of the cosine potentials, effectively we realize the flat direction of the potential, and along this flat direction, that could be a dark energy by contributions from two fields. On the other hand, we have another field, another direction, mass eigenstates that could be massive more than dark energy case. That's why this model predicts linear combinations of two fields. One is the nearly massless quintessence dark energy field. The other is the massive field, dark matter field. So this model connects the constraints between the dark energy and dark matter of our universe. And so let's introduce the action from couplings. And so from this action of couplings, we can get the effective coupling constants of the action dark energy photon coupling and action dark matter photon coupling. And by considering the alignment of the multiple potential, we can effectively amplify the anomaly coefficient by looking at a small epsilon. So that's why this mechanism it potentially resolves the large anomaly coefficient problem. And also we have another coupling constant, action dark matter to photon, from these models. And once we constrain the action dark energy photon coupling coming from the birefringent angle, so we can also constrain the parameter region of the axiom dark matter photon coupling. So this is the final slide. So this is my this is the main result of this study. So once we choose the axion dark energy mass, it also predicts a parameter region of the axion dark matter photon coupling with respect to the axion dark matter mass down to the 10 to the minus 22 electron volt up to the, for instance, order 1 electron volt. And so depending on the value of the axion dark energy, it predicts a large value of the axion dark matter photon coupling. So they are testable with current measurement or next generations axion dark matter missions. And in some areas, so they overlap, the QCD action bands. So it would be interesting to think of any connection between this mechanism and QCD action. Okay, so let me summarize my talk. So actions are promising candidates for the dark sector of our universe. And up to now, a variety of experimental astronomical observations methods have been proposed by looking at action photon conversions. On the other hand, so we have another method to search for actions by looking at the photons birefringent measurement. And so recently we have suggested experimental scheme to search for action dark matter by using the optical cavities used such as in the gravitational wave detectors. And recent measurement of the CMB cosmic birefringence also gives us a very interesting tantalizing hint for the action physics, especially actions of dark energy. And so I have proposed a model of the multiple action field, and based on the multiple action scenario, this observable can connect the constraints not only the dark energy but dark matter axiom. And so we are looking forward to the more exciting discovery to the coming in next decades. So that's it. Thank you very much for your attention.
Thank you very much, Ippei. Yes, so
Mhm. Mhm.
In relation to fuzzy dark matter, that with other masses like that we have in the standard cold dark matter model in relation to dwarf galaxies. Profiles and other astrophysical, another mass standing the profile of cluster of galaxies. So, so my question is, how piece of axion masses and scenario.
Thank you very much for asking. So let's see. So in this model, so we predict two fields. One is dark energy. The other is once we choose the preferable parameter sets of the model, we predict action dark matter mass with let's see, arbitrary mass range, for instance. And of course, we could realize the fuzzy dark matter mass corresponding to the 10⁻22 electron volts. And what I am feeling it will be interesting with that. So this dark matter, when we think of this dark matter, that interact with the dark energy, right? So that's why, so so it'll be interesting if we think of the original scenario, such as the the small scale crashes or something like that. The fuzzy dark matter can play a role of resolution. So that would be interesting if the considering the interactions between dark matter and dark energy. And so when what happens if we could think of the time evolution of the, for instance, the fuzzy dark matter or something like that, coupled with each other? Is that any possibility to that coupling might deviate from the standard prediction from these fuzzy dark matter or dark energy? That's my one of my outlook to develop. Yeah, my study. Thank you very much.
More questions? I have a few. You don't have so precisely related to the last topic that you were discussing, this common explanation of the dark matter and dark energy by calling different action fields. If I understand correctly, at the end of the day, this is like having a single fluid that changes in time its equation of state somehow, from behaving like a dark matter at some epoch and dark energy at another. In particular, you are saying that now the fraction that behaves like a dark energy is like what we understand as a quintessence model in the typical description. Is there any relation between the values of the equation of state of the dark energy with that of the mass of the axion field, or they are independent parameters? In other words, is there any fixed relation between the mass of the axion field and whatever value that you get for the equation of state parameter?
Okay, thank you very much for asking. Actually, they are related to each other. So, for instance, let's see. The equation of state, when we consider for instance, the equation of state at dark energy, so it's related to the the slow roll motion of the axion, and it's given by the shape, flatness of the potential, and this flatness is given by the cosine function, but it's related to the mass itself. Once we consider the very, very ultralight mass, the flatness becomes the slope becomes very, very flat, which means that the action can play a role of almost cosmological constant. The equation of state, so it's almost -1. And once we consider the, for instance, the much higher mass regime, the equation of state might deviate from the -1. That's just like the equation of state for the quintessence. And so also we have another field in this scenario, the heavy mass axion oscillates in time, and effectively it leads to the non-relativistic fluid of equation of state. It's 0, but actually, so there are two fields. If their interactions are relevant, that might lead to the another deviation of the equation of state, for instance. That could be a potentially another observable, but so we will need probably a much developed measurement of the equation of state, so dark energy survey, for instance. Yeah.
Okay, thank you. More questions? I have one.
Okay.
We were discussing so far away from us that is proving the acceleration of the universe, or is because the actual masses that you are exploring? I mean, is the mass of the axion field what define whether it is considered as an explanation of dark energy and dark matter, or is any other reason what tells you, okay, this is caused by dark matter, this is caused by dark energy, always as an axion field?
So usually, sorry, as if I understand correctly your question, so once we consider the typical mass range of the axiom, so we can find it's dark energy or dark matter. So that's this is because for instance, so it's important to compare the probably it's better to go back to the first slide. So let's see. So it's better to think of the relationship between the Hubble parameter and the mass of the axiom. And if the mass is smaller than the Hubble reflection term becomes dominant. It's almost frozen. It's almost frozen, which means that the axion can play a role of a cosmological constant effectively. That's just like axion as dark energy. And we know the current value of Hubble parameters. And from that, from the observations, we identify the mass regime of the axion as dark energy, less than 10 to the minus 33 electron volt. On the other hand, so we have if the mass is greater than the Hubble scale, so it oscillates in time and can play a role of dark matter. And the lower bound of the axiom mass as dark matter is now, so on a debate. So let's see. One stringent constraint coming from the CMB measurement. So when we consider the action dark matter with much, let's see, action mass with less than 10 to the minus 24 electron volt of similar magnitude, it modifies the CMB spectrum. That's totally so that's forbidden by the measurement. So that's stringent constraint. But so the fuzzy dark matter regime, that's still, I think, on the debate and not confirmed. What is the typical bound around the 10 to the minus 22 electron volt? Yeah. So is that the answer to your question?
I think is the mass. behavior of the other.
Yeah.
Okay. More, yes, Belén.
If I understood correctly, you said that that's on the cosmic refringence, which is the time scale for that. Could we measure? Did we measure in several years?
Okay, thank you very much. So time scale is characterized by the mass, just like the the Compton wavelength corresponding to the Compton wavelength, and the frequency is given by the mass over 2 pi, and so when we normalize it's 10 to the minus 14 electron volt, where the action can play a role about dark matter. The corresponding frequency is around the order of 1 Hz. The frequency period is around 1 second. And when we consider the much lower mass regime, for instance, 10 to the minus 22 electron volt action can play a role of fuzzy dark matter, and corresponding frequency is around order of year. Frequency period is order of year. So that's why if we want to measure this, deviation of the polarized plane, the birefringence time evolution, we need a long real-time measurement to distinguish the oscillatory feature of birefringence angle. So, but when we consider the higher mass regime, just like the order of 1 Hz or millihertz or kilohertz, we don't need to think of much longer measurement. But birefringence angle is inversely proportional to the mass of the action. That's why the magnitude is decreased at a higher mass regime. Yeah, that's problem. That's why the cosmic birefringence is really relevant. The cosmic birefringence is really relevant to a very ultra-wide action. Yeah. So let's see. To probe the ultra-wide mass, we need a long time cosmological distance, for instance. But in the case of the gravitational detector, we can effectively amplify the the round trip of the photons. We can effectively amplify the length of the optical path. So that's why we can measure the very light action mass regime, even if this scale is not so long, comparable to the astrophysical measurement. But anyway, so yeah, so I want to answer to your question. So depending on the the mass, depending on the different frequency period, we have to think of the several approaches to birefringence measurement.
Thank you for your talk. My question is 38. I can see that you go to very small values of the coupling between the axion and the photon. Is there any theoretical or empirical lower limit at the small values?
Okay, so actually not so strong bound, but once we consider a simplest scenario of the axion dark matter, so and once we consider, let's see, the simplest order of unity anomaly coefficient, we can identify the parameter regime of the action-like particle as dark matter. But that's model dependent, not so strong bound. Yeah, that's the reason. And then this measurement abracadabra, that's projectable, is very ambitious experiment, and they cover the wide range of the action mass, and this limit just correspond to the typical parameter space, the action-like particles as dark matter. But it's not a lower bound,
Any further question? No? So thank you very much, Ippei.
Thank you very much. Thank you very much. Muchas gracias.